Hello everyone, welcome back to I think the last lecture of ST421. So today we will discuss one very I think important technique, which is the multivariable transformation, the Jacobian. So this is section I think 6.6 of your textbook. So whilst optional, I think it is still very important for materials that you may want to see in say like 422. So I would encourage you to take a look at the material in this section. So the multivariable transformation for Jacobian is in a sense based on a change of variable theorem that we have already seen in the bivariate case. So it's a change of variable theorem of multivariable calculus. And it is very useful for, once again, deriving the density of multivariate transformation of continuous random variables. So the setup is a little bit more, say, complicated than what we usually see. So let's go through it maybe step by step. We have a collection of m random variables, x1 to xn. Suppose they have joint PDF f x1, x2 up to xn. And suppose I have this set S here, which is the support of x. What that meant is that the probability that my random variable x, which is n variate, belong to the set S is equal to 1. So, for example, the set S could maybe be equal to the same as the real line, n copies of it. Or maybe the set S could maybe be something like just the positive numbers and copy of it, or so on and so forth. So now suppose I have n other random variables, u1 to un, each of which is a function of x, of the xi. So for example, ui is some function gi of the variables x1, x2 up to xn. And now we want this collection of u to satisfy the following properties. So the first property is that the mapping from x, which belongs to the set S, to the collection u, which is now u1, u2 up to un, belonging to subset T, we want this map to be 1 to 1. So it's an injective map. Furthermore, if I look at the xi and I want to invert it, so I want to have the inverse function, which goes from the u, 1 u2 to un, back to the xi, I want this function hi to be continuously differentiable. So this property here, or this requirement, is a little bit strict, but generally speaking, it will hold for most of our application. So the inverse function is continuously differentiable. And then finally, if you have that, then you can construct this n by n Jacobian matrix, which just takes the Jacobian, the ij entry of this matrix, is the partial derivative of the ith function with respect to the jth variable for the u. So the partial derivative of the inverse function hi with respect to the j variable for the u. And I want the determinant of this Jacobian matrix to be non-zero for all my values u1, u2 to un belong to the set T, for which it is equal to, so as we said earlier, T here is basically the map, the domain of the mapping from X to U. So if you have that Jacobian transformation, then you can easily define the joint density of U of the random variable u1, u2 to un, where now ui is gi of x1, x2 up to xn. The joint density of the u is given by the PDF of the u is the PDF evaluated at the inverse function. So xi is hi of u, the inverse, multiplied by the determinant of the Jacobian matrix, the absolute value. So this is the absolute value of the determinant. It's not just the determinant, it's the absolute value of the determinant. Okay, so this result here is known as the change of variable result in multivariable calculus. And generally speaking, we have already seen the example in the case when you have n equal to 2, which is just the, so for example, in the polar coordinate change of variable. Or if you remember the gamma and the beta integral example in the earlier lecture note. So the general result, this result is in general in the case when n could be bigger than 2. So this result is quite, I would say, powerful, except that, generally speaking, our function g and our function h are generally quite simple. So in the application, we will usually want g and h to be generally simple because, as you recall, everything the determinant of say a 4x4 matrix is not very fun. Not to say the determinant of, say, a 10x10 matrix. So in generally speaking, we do not do it for big N, so we usually do it for small n. And if n is big, then usually we will have to have very special structure, as we see a few examples later in the slide. So this general result is usually never applied in general. So like I said, either g and h are generally simple functions. So as a quick example, so like I said, when the transformations are sufficiently simple. So this is problem 6.64 in the textbook. So I think it's a quite cute problem. So let's try to demonstrate its use with the multivariable change of variables. So I have x, which is gamma, alpha 1 and beta, and y has this possibly different shape, but the same scale. And x and y are independent. And I want to find the distribution of u, which is x divided by x plus y. So we know that x plus y is just gamma alpha 1 plus alpha 2 beta. So what is this ratio of x divided by the sum of x plus y? And the trick to do this is to introduce another random variable v, and then we will have uv is some function, say h1 of xy and h2 of xy, or g1 of xy, g2 of xy, to use the consistent notation. So let's write this as g1 and say g2. And then we can look at the inverse function h1 and h2. So the inverse function turns out to be given simply as follows. So if that's the case, then h1 of uv is just going to be u times v is equal to x, if I define v equal to x plus y. And then h2 of uv would then be equal to 1 minus u times v, which will be then equal to y. So that is the inverse transformation, and you can check that that is indeed a transformation from uv back to xy. So the Jacobian matrix, as we defined, is simply given by this 2 by 2 partial derivative. So the first is derivative of x with respect to u, and that is simply v. the second derivative of x with respect to v, and that is simply u. And for y with respect to u, that is minus v. And y with respect to v, that is over here, 1 minus u. So therefore, the determinant is just v 1 minus u minus uv is just going to be v. So the absolute value of the determinant is equal to v. So the key point then now is that we emphasize is that u, which is in 0, 1, because y is non-negative and x is non-negative. And so x plus y is obviously bigger than or equal to x. And furthermore, v, which is x plus y, is unbounded because both x and y are unbounded. So using these two facts, we can easily have is that the joint PDF for uv is the joint PDF for the inverse x and y times v. So now all we have to do is, as we say, x is uv. So therefore, we have x, the PDF for x alpha minus 1, e minus x over beta. This is the marginal PDF for x belonging to gamma alpha 1 beta. And this is the marginal PDF for y gamma alpha 2 beta. And now using the fact that x is uv and y is 1 minus u times v, you can then replace x is uv and then y is 1 minus u times v. And then furthermore, you will have e minus x divided by beta, e minus y divided by beta, that's e minus x plus y divided by beta, but x plus y is simply v. So x plus y is equal to v. So that's why you have e minus v over beta. And then this is the Jacobian, so you put it here for the Jacobian. And after some simple manipulation and collecting the term that depends on v is here, e minus v over beta. And then they have v to the alpha 2 minus 1, v alpha 1 minus 1, another v, so you get v alpha 1 plus alpha 2 minus 1. And then the part for u is u alpha minus 1 minus 1. And then 1 minus u alpha 2 minus 1. And some simple checking. Let's erase that just to make clear. And so after some simple checking, you will see that this is the PDF, the first part. V has the PDF form for gamma alpha 1 plus alpha 2 and beta. So v is alpha 1 plus alpha 2 times beta. And this part for u looks like the PDF for beta alpha 1 alpha 2. So the joint PDF for uv factors into a product of the marginal for v and the marginal for u. So u and v are independent. So the joint PDF can be factored into the product of two functions, one depending only on v, the other function depending only on u, and uv belongs to 0, 1 times 0 to infinity, so that by chapter 5, we know that uv are independent. So in summary, u, which is x divided by x plus y, have a beta distribution. And v, which is x plus y, has a gamma alpha 1 plus alpha 2 beta distribution. So in the special case when alpha 1 equal to alpha 2 equal to 1, then beta 1 is just uniform. So therefore u is uniform. And that is basically the claim, which I think is one of the example in section 6.6. So you may want to take a look there. But in any case, what we conclude is that u is beta and v is gamma, and they are independent. So as you can see, This example is, you may think it's quite contrived, but in reality, in many applications of the multivariate Jacobian, you can't do something too complicated, because if your function is too complicated, then the evaluation of this determinant would be quite a pain. So let us now take a detour, but a very important detour nevertheless, to talk about the multivariate normal distribution. So in a sense, the multivariate normal distribution is the building block of almost all, I would say, classical statistics. And I think that really understanding the multivariate normal distribution is fundamental for being able to, easily read, articles or papers about the use of statistics in analyzing, classical traditional data. So, like we said, the Jacobian is essential in defining the multivariate normal distribution, and that's one of the most important distribution, I think, in statistics. So the multivariate normal distribution can be defined as follows. Suppose I have x1, x2 up to xn be independent standard normal random variable. So in that case, by independence, the joint PDF of x equal to x1, x2 up to xn would be of the form, 2 pi minus 1/2 will be by independence. Let's write that is equal to the product of I from 1 up to n, 2 pi minus 1/2 of exponential minus xi squared divided by 2 by independence. And we can write this obviously as 2 pi minus n over 2, and then exponential of minus 1/2 summation I from 1 up to n of xi squared. So this is the joint PDF for a collection of IID, independent and identically distributed, standard normal. Okay, so that's the first step. So let's think about that then. So we've handled this collection of standard normal, and now I let my A be a n by n matrix. Now I defined my collection of random variable u1, u2 up to un quite simply. Ui is some constant ci plus some linear combinations of the xi. So for example, u1 is c1 plus maybe a1j, and let's say plus a11 x1 plus a12 x2 plus plus a1n xn. And then u2 is another linear transformation, c2 plus a21 x1 plus a22 x2 plus plus a2n xn. So each of the ui is a linear combination of the xi. So I will let aij be the ith entry of this n by n matrix boldface A. So the map from x to u is 1 to 1 if and only if the matrix A is invertible, because then I can then write, if in that form, I can think of my matrix U, the vector U, as U1 up to UN, can be written as a matrix A times the vector X1 up to Xn, plus the vector of constant C1, C2 up to Cn. In which case, my X1 up to Xn can be written as A inverse times U1 up to Un minus C1 up to Cn as inverse transformation. And this is what defined if and only if A is invertible. So that is what we meant. So suppose A is invertible and we denote by B, which is the inverse of A. Then to go back from U to X, I just have to do the linear combination here. I get the U J minus the constant Cj, for which I shift, and I multiply it by the inverse transformation Bij, and I sum it over J. So that defines my Jacobian transformation. So as we see here, the inverse transformation is given by B. So therefore, I could easily say what is partial of xi with respect to partial of uj. Well, that is simply Bij. So the determinant of my Jacobian, determinant of Ju, is simply the determinant of my matrix B. And so that implies directly that the joint PDF for U is of the form the joint PDF for X multiplied by the determinant of B. And because the xi are independent, or rather because of the xi are independent, earlier we saw that their joint PDF looks like this. And so now I just have to multiply by the determinant of B. And because B is A inverse, the determinant of B is the same as the determinant of A, 1 divided by the determinant of A. So the determinant of B is 1 divided by the determinant of A. And so the only thing that you have to be careful about is to note that this x here, x1, x2 up to xn, is a transformation of the U. So in that sense, what I said is that xi is summation over j of Bij uj minus cj. So that's how we go from the U back to the X. And this case, the reason why this works quite often is just because, like we said, the determinant of the Jacobian is simple to calculate. And that's just because the linear transformation A, or transformation A, is a linear transformation. So this may seem a bit, say, abstract. And this is where I can safely tell you that when you start to work with the multivariate normal distribution, in many cases, you'll be working quite abstractly. You'll be working in terms of like matrices and vectors product. We will rarely ever write out the expression exactly once we work a lot with it. So that is why the multivariate normal distribution kind of like require a very solid background in, say, linear algebra. And so that may be a little bit outside the scope of our current class. But like I said, if you ever want to do more, say, statistics, a good understanding of the multivariate normal distribution is essential. So let's see a quick example. This is section 5.10 of your textbook. So suppose I have the case of very two simple case, x1 and x2. I have two standard normal random variables. And now I define u1 to just be some linear transformation of the x1. So just sigma x1 plus mu1. So u1 is sigma x1, sigma 1, x1 plus mu1. So by default, that will be normal with mean mu1 and covariance matrix sigma 1 squared marginally. And then now I define u2 to be sigma 2 times rho of x1 plus square root of 1 minus rho squared times x2 plus mu2 for some number rho in minus 1 to 1. This is known as we'll see later, this is known as the correlation between u1 and u2. So what then is the joint PDF for u1 and u2? And this is once again an exercise in the multivariate Jacobian. So we just need to invert back. So from u1 and u2, and I want to go back to x1 and x2, I can easily do that as follows. x1 is simply u1 minus mu1 divided by sigma 1. Looking at this equation, once I have that, then x2, I can substitute x1, I can substitute the expression for this expression into this expression and derive x2. So x2 is simply given as follows. So that is the inverse transformation from u1, u2 to x1, x2. So then what then is the determinant? What then is the Jacobian? Or the determinant of the Jacobian? And that is easy because we see that partial x1 over partial u1 is just simply 1 over sigma 1. And partial x1 over partial u2 is 0 because there's no dependence. And a partial x2 with respect to partial u1 is going to be minus rho over sigma 1 square root 1 minus rho squared. And then partial x2 with respect to partial u2 is now going to be u2 divided by sigma 2 square root 1 minus rho squared. So the Jacobian inverse transformation, as we said earlier, is what we say here. These quantities. And so the determinant of the Jacobian is going to be 1 over sigma 1, sigma 2, just this term, and then this term is 0. So 1 minus sigma 1, sigma 2 times square root of 1 minus rho squared. And so the joint PDF for u1, u2, is then the Jacobian, this part is Jacobian, times the exponential of minus x1 squared divided by 2 and x2 squared divided by 2. But by definition, where we say x1 is u1 minus sigma 1 minus mu1 divided by sigma 1, and x2 is what we say here. After some simplification, this is the joint PDF for u1 and u2. And this expression is, I think, quite a monstrosity. You have 5 parameters floating around. Sigma 1, sigma 2, rho, mu1, and then mu2. So the bivariate normal distribution, this is known as the bivariate normal. So take a look at section 5.10 of your book. 5.10 of textbook. It may look, say, mysterious, but really it is quite simple. It looks complicated, but it is nothing more than this transformation of two independent normal. So like we said, just a simple transformation of simple random variables can give you things that looks quite magical or messy. And so in any case, using this construction, we can then now look at the distribution or the conditional distribution, say, of say like u2 given u1. So if you look at the exercise in section 5.10, they will look quite scary, because if you're not careful, you will have to carry out a lot of integration. So if you base it on this PDF and you say you want to get, say, the marginal of u1, then you have to integrate the joint PDF f of u1, u2 with respect to, say, du2 from, say, minus infinity to infinity of this expression. And that doesn't seem like something that you want to do in your spare time. But if you use this form, it is quite simple. So what is the marginal of u1? Marginal of u1 is, as we said earlier, just normal mu1 and sigma 1 squared. Marginal of u2, because it's a sum of independent normal, marginal of u2 is going to be normal with mean mu2, because x1 and x2 have mean 0. So this part, the expected value of this part is going to be 0. So therefore, no more mean mu2. And now the variance will be, because they're independent, the variance of u2 will be the variance of sigma 2 rho x1 plus the variance of square root 1 minus rho squared sigma 2 of x2. And that should be, as we can easily see, just to write out, variance of u2 is variance of let me see, sigma 2 rho x1 plus variance of sigma 2 square root 1 minus rho squared x2. And by independence, that's just going to be sigma 2 squared rho squared variance of x1 plus sigma 2 squared 1 minus rho squared times variance of x2. But variance of x2 is equal to 1. And so this becomes sigma 2 squared. So marginally, u2 is no more mu2 sigma 2 squared. And we can derive this without the need to do any integration. So that's the power of this linear transformation. Okay, so let us go back and talk about our next aim, which is to derive the conditional distribution. Okay, so we want to derive the conditional distribution of u2 given u1. So if I told you the value u1 equal to little u1, in which case that's the same as, based on this transformation, that's the same as telling you that x1 is u1 minus mu1 divided by sigma 1. Just because of this linear relationship between u and x. So if that's the case, then looking at this form here, I can just say that rho of x1, which just becomes rho of u1 minus mu1 divided by sigma 1. So if I multiply by sigma 2, that's just this part, once I told you that x1 is equal to this term. The remaining is just this sigma 2 dependency on x2 plus mu2. So in that case, because x2 is standard normal, it has mean 0 and variance 1. So therefore, the distribution of u2 condition on u1 equal to little u1 is just mu2 here plus this term which depends on little x1. And then the variance is still 1 minus rho squared times sigma squared. So this should be 1 minus rho squared, 1 minus rho squared times sigma squared, not 1 minus rho everything squared. And then using the same trick, you can reverse the rho of u1 and u2 to show that the distribution of u1 condition on u2 equal to little u2 will be this distribution. So in a sense, what we have shown here is that the distribution of u2 given u1 equal to u1 has a mean that is transformed by the shift between u1 and mu1. And the variance is a bit smaller. So the variance is now 1 minus rho squared times sigma 2 squared. And that is basically the relationship, the conditional PDF of u2 given the value of u1. So if you want a quick exercise, you should go back and take a look at the exercise in section 5.10 and see how you can derive them without needing to do any integration. That should tell you the power of this linear transformation trick for the normal distribution, multivariate normal. Okay, So let us go back to revisit student T. So you will see this technique a few times in, say, chapter 7 of your textbook, which will be the topic of ST422. But the problem is that your textbook never really kind of like prove this result. So they just give out this result as if it is a little bit kind of like magical. But as we will see, there's nothing magic about it. It is maybe not easy, but there's nothing difficult about deriving the results of chapter 7. So let us now show one of the most fundamental results in classical statistics. That is that the sample mean in a sequence of independent normal random variables is independent of the standard deviation. And so if you take, say, like more, say, elementary statistics class, you would have talked about, say, the student T statistics, where you take the sample mean minus, say, the supposed true mean divided by the estimate of the standard deviation, say, divided by n minus 1, and you claim that this is student T with n minus 1 degrees of freedom. So let's prove that. So the proposition goes as follows. Let x1, x2 up to xn be independent and identically distributed random variable normal with mean mu and variance sigma squared. We will claim that the sample mean, x bar, is independent of the sample standard deviation. Standard deviation. So the sample mean is independent of the sample standard deviation. So this may be problem 13.93 in your textbook, but it's unlikely that any of us will ever take a look at chapter 13. So let us do it right now, instead of waiting for so long.